about my teaching stuff. Okay, good morning again, guys. Any questions about the syllabus? Any questions about the syllabus? Need to keep the syllabus handy, reread. I give you recommendations, okay? Just like instructions in the workbook, okay? Don't just read them once and then continue on and then often don't follow them, lose points, etc. Or lose out on the important recommendations, okay? If you like my recommendations on how to do well, I've supplied some, okay? All right, guys, let's get started. Any questions about material from Monday? We've got NMR lectures on video. Yeah, how are we doing NMR? Hopefully you're getting started. Hopefully you got started maybe before class, yeah? Before the semester started. Okay, chemistry of alcohols and ethers. All right. And we ended with making tosylates. Any questions about that? The first look at what type of mechanism? Additional elimination. Okay, it's a new type of substitution mechanism. It's not SN1. We never saw any cation anyway, carbocation. We were attacking sulfur, but there's never sulfur cation. It wasn't SN2 because we didn't directly, when the nucleophile attacked, did it directly kick off that chlorine? No, so it wasn't SN2. We didn't directly kick off the leaving group. New mechanism, additional elimination. We'll see it more and more. It is a substitution mechanism. What was the rate determining step? Did we identify the rate determining step? Typically, the nucleophilic addition is the rate determining step. Then the elimination tends to be thus a faster step. Okay? Nucleophilic addition, RDS. Yeah? The first page. We look to next to the last one with potassium iodide, sulfuric acid. How do we do on that mechanism? Was that SN1 or SN2?
SN2.
SN2? Mm-hmm. How do you know it's SN2? Because SN2 comes with inversion. Yes. Product of inversion. So what was the first step of the mechanism? Apparently the OH is left. It's gone. Leaving group. How do you make OH better? Leaving group? Protonated with strong acid. Is there a strong acid available? Yeah, sulfuric acid. Okay. Then after we protonate it, what was the next step? Everybody can protonate an alcohol. I'm going to skip that step. What was next? I minus then comes in here and kicks it off. SN2, right? What does that give? Gives that, right? With inversion? Okay, plus what? Plus H2O, which was the leaving group, right? Okay, pretty straightforward. Note that we didn't have to use HI. HI would have supplied the H plus and the I minus all together. You don't have to do that. You can supply the needed ingredients with other reagents. Some strong acid and maybe a potassium iodide salt. One below. Now this should have indicated something here. Actually, it should not have. Should not have. Supply mechanism down here. It's a little more vague. What's the mechanism down here? It's actually the same exact reaction, and instead it uses Cl minus as a nucleophile, right? Mechanism down here. Why say SN1?
Because it'll protonate the OH and then that'll leave, and then you have a hydride shift because you want a tertiary carbocation, not a secondary. And chlorine is not a strong enough nucleophile. Oh, it's kind of in
Chlorine
the
is
middle.
borderline. You could see some
It's
SN2s
borderline.
with
Yeah.
chloride being a
There's some
nucleophile. But it was said right here. How do we know it's what was the key thing we see here? There must be a carbocation rearrangement. Otherwise, how's the nucleophile going to get over on the other carbon? The only way that's going to happen is to have a carbocation that then rearranges. And since we have to have a carbocation, this must be what? It's carbocation chemistry. And if you're doing substitution with carbocation chemistry, it's SN1. Okay? So we got rearrangement. I'm not going to go through that, but everybody see what we're doing here? You guys see carbocation rearrangements in organic 1? Yeah? Okay. Should be pretty straightforward. And so the fact that we got carbocation rearrangements sort of tells you what the mechanism had to have been. You don't get carbocation rearrangements. They're so-called skeletal rearrangements with SN2. Okay, so we see mechanism for making tosylate. And tosylate's a good leaving group. The OTOS, that's the tosylate. Okay, good leaving group. And so nucleophiles now can, come in here. This may be charged, may not be. Come in here and attack this. Just kick that off. We don't have to protonate the tosylate. In addition to tosylate, there are a couple of others. Mesylate, that's where instead of a toluene group, it's just a methyl on the sulfonyl. Mesylate comes from methyl sulfonyl, shortened to mesylate. Same thing. We also have triflate, where it's a trifluoromethylsulfonyl. Trifluoromethylsulfonylate. It's called triflate. It's actually the most reactive because these fluorines really pull and stabilize the O- that eventually leaves. Triflate is very common at the upper level in organic chemistry. Probably not going to see these in your textbook. Could. Tosylate's the most common at the introductory level. A couple of similar reagents are these here. Dimethyl and diethyl sulfate, right? Because if we just had this, and these being minuses with lone pairs all over the place, what is that? Yes, sulfate, right? Right? SO4 2 minus, sulfate. You learned it in what, 3rd grade? Okay. And then what can you put here? Like sodiums, maybe, yeah? And what is that? Sodium sulfate? Right? Which you use when, where, how? Yeah, that's right. To dry your extracts or something, anhydrous sodium sulfate. Okay. Right? Ionic. But instead of sodium ions here, what if instead of putting ions here, we make something covalent, maybe like a methyl? It's possible. What do you want to call that? Dimethyl sulfate. But it's all covalent now. Okay? Or diethyl sulfate. That's what we have here. That's where the names come from. Okay, they're diesters. What if instead of O-methyl it was OH? Be H2SO4, be sulfuric acid. These are so-called esters of sulfuric acid. Okay? But one end is just like a tosylate. If over here was a toluene, okay, like this, that's a propyl. But if that was a methyl, and over if this here, if that was toluene, it's just like that. And so nucleophiles can attack the methyl and kick that off. Analogous to this here. Now you can actually attack the methyl over here and kick it off here this way as well. So it's kind of doubly reactive. It typically only reacts on one side though. But these are analogous. Very common. One reason they're very common is because they're very cheap. They come from sulfuric acid. They can easily be made, and you can buy like a big jug of these very cheap. Okay. So they're very common for supplying methyl group, or ethyl group. All right. So a nucleophile can attack methyl, ethyl. What's a general name for methyl groups, ethyl groups, propyl groups? Right, alkyl groups, right? Okay. And if something's going to supply an alkyl group, what do we call that thing? What type of reagent is that? Alkylating reagents. Okay, right? Terminology falls into place, right? These are common alkylating reagents to supply methyls and ethyls. They also tend to be pretty toxic. Okay? Because, particularly methyl, even diethyl sulfate tend to be kind of toxic because the tosylate is a great leaving group. They're alkylating reagents. Okay? But they can alkylate your DNA or proteins in your body. And this can lead to bad things like cancer. Okay? Or alkylate the proteins in your eyes and then start making your eyes very like, what's going on here? You do it enough to cause irritation. Just for some vapor around. Okay, how do we do over here? All right. How do we do over here? Product of that reaction top. Somebody got it? Somebody got it? Somebody got it? Well, let's see if it's right. I'm not going to live too close because I'd have to. Everybody got it? How are we doing? Next page. Next page. How are we doing?
What did you get?
You got it? Again, guys, when we come to class, it's showtime. All right? Anybody do any performing? Stage, acting, singing, anything? All right? Yeah? Do you practice beforehand, or do you show up on the day of the performance? And all right? Showtime, guys. What do we got here? 2 separate steps, okay? A lot of times students are like, well, we're going to have time. No, this is not here. That's next week. Step 1, what does step 1 do to this? Converts it to a tosylate, right? We went over the mechanism. So let's show the tosylate. What would it look like? You can go through mechanistically. It would be O-tos, and this would be D here, deuterium. Yeah? Whenever we make the tosylate, is there any change here in this stereochemistry? No, because when you make the tosylate, you do no chemistry at that carbon over there. It's the oxygen attacking the sulfur. There's no change. Okay, so that's step 1. Now we come in here, what is this, sodium azide? I showed this in organic 1. You guys seen azide before? Okay, it's just a nucleophile. It's N3 minus. But let's show the full structure. Okay, can you show a loose structure of azide? Actually, 3 charges. That's a good loose structure for N3. What's the charge of the N3 here? Negative, because sodium is positive. Okay, it's net minus. Okay. One end is nucleophile. Typically only reacts once. But the N minus attacks here, kicks that off. It is SN2, right? That's a primary carbon. Because a D is like an H, right? But a D just allows for stereochemistry in a primary carbon. Because it's different from the H. But it's still considered a primary carbon. And so what is this going to give? What do we got? 3 carbons, 1, 2, 3. 1, 2, 3. I can just show this condensed, the N3 group that's bonded there. You should be able to show full structure. It's basically the same thing, except this nitrogen is now bonded to the carbon. So you can show that out if you want. Everybody good? And what do we do here? SN2? All right, SN2. Everybody good? Elizabeth?
So, since it's SN2, would there not be an inversion?
No, yeah. SN2 comes with inversion. We did inversion.
Could you draw it the other way?
Here's my right hand.
Oh,
Okay. Okay. Now hold on. Now what is that? Okay. How about this? What is that? Right hand. Okay. How about that? What is that? Okay. Show it however you want. As long as it's the right hand. Now if I ask you to show me your right hand and you show me your left hand, then you're going to be wrong. Okay. Now I don't care how you show the product. It just needs to be inverted. You don't think it's inverted?
I was looking at the wedge and the wedge.
Okay. Well, as I pointed out in Organic 1, you can't fall into the trap of thinking inversion is always bolded dash or the other way around. Inversion. What is the RS here? Real quick, RS.
R.
Oxygen 1, carbon 2, D 3, H in the back 4. R. What is this? Nitrogen 1. This only works when the leaving group and the new group have the same priority. But that's 1. Carbon 2, D. What is this? S. It is inversion. But again, what I just did works 99% of the time. I don't want to blow your mind or anything, but you can do an inversion where S becomes S. Inversion is a process of backside attack. How you can get S, how you can get R to R and it still be inversion? If the new group does not have the same priority as the group that left, you could end up with SR going to R, but it still be inversion. Because what if the thing that attacked was an H for somehow? Then this would be an H, and it would no longer be high priority. And it may end up being still R. But that doesn't mean that the H minus or nucleophile didn't still come in backside and do an inversion. But that's rare. Most of the time, you are going to look to go from R to S or S to R. But don't fall in the trap that it has to be bold to dash. Depends on how you show it. Somebody said, can I show? I could have showed this product another way. I could have showed this. That's a D. You like it better now? Like it better now? Okay. Well, this is also S. Those two over there are the same thing. Okay? How about the one below? What's NBL lithium going to do to this? What type of chemistry do you recognize from Organic 1? Alkynes, terminal alkynes. The CH of an alkyne has enough acidity we can do acid-base chemistry, yeah? Right? There's H here. N-butyl lithium is just a butane anion. It's just butyl anion and a lithium plus. Very strong base. This takes the H. This stays behind. Acid-base reaction, remember your acid-base mechanism? And that gives what? Gives that acetylide anion. Remember the miner's helmet? Talked about that in Organic 1. Okay. In butyl lithium, another common base here is sodium amide, sodamide, NaNH2 minus. That's a common base often used for. Yeah. What do we now have? A good nucleophile. What is this? We just talked about dimethyl sulfate, right? And so we have right? And so this attacks the carbon, kicks off what looks kind of like a tosylate, right? So what's the product? Yeah? Instead of CH3, I did ME, methyl, which I commonly do, yeah? Methyl group on the, okay? We methylated the alkyne. Methylating reagent, alkylating reagent. Well, we first had to make the stronger nucleophile, the good nucleophile, right? Okay. And now the terminal alkyne is now a internal alkyne, or non-terminal, right? Common reaction of terminal alkynes is we can turn them into nucleophiles and alkylate them. Yeah? A lot of reviews from Organic 1. Everybody agree? Reviewing? C, reaction of alcohols. It's kind of what we're doing. Substitution. Different substitution here. Instead of using HBr or something, there are other reagents we can use. Instead of using HCl, you can use these reagents. Either PCl3 or this one here, which is called thionyl chloride. We'll see it again and again a couple of times. Okay? Or we can do PBr3 to make the alkyl bromide. These are analogous. Typically you don't ever see SOBr2. You don't ever see that. All right? Analogous. Very similar, except instead of activating this by protonating it, instead, I'm going to do it with SOCl2 because I think it's more useful. Okay? This is here. Okay? Thionyl chloride. It's in your textbook. Sulfur, of course, has a lone pair, right? Lewis structures. You know that, right? Okay. What if that was a toluene group over there? What would this be? Actually, not quite. Similar to tosyl chloride. Tosyl chloride has 2 oxygens on the sulfur. This only has 1 oxygen. All right? But still, this can attack the sulfur. All these electronegative groups, the sulfur is kind of partial positive a little bit. And still, the first step is this attacks. What do you want to do here? Do we kick off with chlorine directly? Or do we break the weaker bond? Break the weaker bond. Okay, so move these up here. All right, analogous to making the tosylate. And this is going to give oxygen is now bonded to the sulfur. H is there. We didn't lose the H. That's a positive charge. We just made this bond to sulfur. But electrons up onto oxygen. Okay? That's how we get the third lone pair. It becomes minus. But the sulfur has 2 chlorines, right? And what do you want to call this step? Nucleophilic addition. Okay? What would you do next?
Bring your electrons back down.
Typically, driven by entropy, this thing's going to want to kind of go back to less charge and also split apart. These electrons can come back down. But what's it going to kick off? What's the better leaving group here? Is this a good leaving group? Protonated oxygen, yeah. Good leaving group. Along the way, we'll have to take care of the proton. Okay? And I'll say that, and we'll do that more and more. There's no base here. There's nothing to take care of the proton. If this came down and kicked this off, this group off, where would you go to? You go back here? Yeah. See, that could be equilibrium. You can go back and forth. But sometimes, instead of this getting kicked off, what if the chlorine got kicked off? Can chlorine get kicked off? Yeah. And so it has another pathway to go. And if that gets kicked off, what do we get? Oxygen We reformed the double bond, and how many chlorines left on the sulfur? Just one. And there's an H here, plus what? Cl minus. And at the very end, Christina asked as we were leaving, when we make tosylate, can the Cl minus come in and react? Yeah, remember that? And I said, okay. Well, guess what? Here it is going to react. Because how do we get this? You've got to get a chlorine on that carbon. Is there an opportunity to do it now? We got a nucleophile. Is that a good leaving group, that oxygen? It's protonated. See how we generated a protonated oxygen in this mechanism? It's there. At this point, this comes in and bam, kicks that off. What does that give? It gives product, but importantly, plus what? I'm going to do this. Using thionyl chloride, we get that plus SO2 plus HCl. There you go. There's your balanced line reaction. But how? Because when this attacks, this gives what? That? That's the leading group in that, yeah? But that's not what I showed up there. That's because this thing here decomposes. Question?
Well, I was going to say, does it decompose to where, like, the H?
Okay. And this is important moving forward. We'll say this a lot of times. This is the first time, okay? It was said on January 8th at about 8:25. Anytime you can make a pi bond and kick off a leaving group, that's typically easy and fast and going to happen. Okay? And what happens here is, at this point, this doesn't survive. This is not the end product. We've already made our organic product. But how do we get these other two byproducts? Anytime you can make a pi bond, this moves in to make a double bond, a pi bond, and we kick this off. Okay. A common thing throughout chemistry, and we'll see it again and again this semester. What does that electron movement give? Basically, it's just, what do the arrows mean? WDAM, right? We have double bond sulfur. We don't lose the H, it's not magically gone. The oxygen's now positive when that happens. What's left on the sulfur, other than that? Another double bond to oxygen. And yes, there's a lone pair here. There's a lone pair the whole way through here. Yeah, plus what? Cl minus. Everybody seeing what's coming next? How do we get the final products? This then takes the H, leaves that behind as a lone pair. What does this give? It gives a 2. Because you know the structure of HCl. What's the structure of SO2? It's that. Right? You see how this, when it takes the H, it gives that. That's SO2. Okay? You see how it all falls into place if you know how arrows, once I show you the arrow movement, it's all there. See, this is one molecule. This is driven by entropy. One molecule breaking into two. But also, what did I say? Anytime you can make a pi bond like this, kick off a traditional leaving group, we're going to do that a good bit. All right? So, we've already seen two things that we're going to repeat. A new substitution mechanism, addition elimination. We've actually done that twice now. When we made tosylate, and we did it over here, right? Nucleophilic addition, where was the elimination? Right here. And then back down, eliminate. So this was the elimination. That's how we got here, because it used to be a chlorine on this, it used to be another chlorine on this sulfur, now it's the oxygen. So we substituted off the chlorine, but we did it by an additional elimination mechanism. Question?
Is it possible to have an intramolecular attack where the Cl would come and take the hydrogen, and then the electrons would transfer onto the oxygen, forming a double bond, or would have to be in that exact way that we did on chlorine?
First off, I've already said this before, I'm going to say it many times. We're going to have to figure out how to take care of the proton. Dealing with what you're asking. Can we do it another way? That's what you're asking. And the answer is sometimes, often, yes. So dealing with the proton is what I'm saying is we got to figure out how to do it. And it can vary. Dealing with the proton, that's what you're asking about. So you're asking, can what take this H?
The chlorine within...
The chlorine?
Yes, as it is right now.
Here?
Can
Well,
it
it's
do
already
an
bonded. A bonded
intramolecular-
chlorine is not that basic.
It doesn't do that? Okay.
No. I mean, theoretically, again, it's perhaps, you can make an argument, but I'm going to give you a counter argument. It's not that basic. I mean, if it is, I mean, HCl, this is not going to want to take another H until, but Cl minus, yeah. Even that's weakly basic. I mean, Cl minus doesn't like taking H's. If it did, this would not come this way. Right? What does HCl do? It ionizes. If this liked to take an H+, it would just come back. And if it went back, then it wouldn't be completely ionized, and then we wouldn't call it a strong acid. Right? So, perhaps, but I don't think, again, there's many sort of slightly unknown things about mechanisms, but I don't think I want to show that. Again, we're doing some general concepts. Thionyl chloride. So instead of using HCl, where we protonate, okay, so these are reagents. These reagents are particularly good when your alcohol is primary. Okay? They're better for HX primary. Because this tends to be a better leaving group than just water for SN2. Because we did do an SN2, right? If you wanted to make an alkyl halide by an SN1, we'll just use HCl or HBr. Traditional. Okay. So these tend to be better. I'm not going to show these. You can try it on your own. Think about Lewis structure. Think about how it might be a little different than what I showed. I showed this thionyl chloride because we will see thionyl chloride along the way more. So those are some reagents. So we can put this into some synthesis. Okay. In the end, you know mechanism, but you also know what's PBr going to do to this alcohol. It converts it to what?
Alkyl
So you just need to recognize reagents. So reaction 1 gives what?
halide.
Alkyl bromide. What type of stereochemistry though?
Inversion.
Does chemistry take place at the carbon when you react with PBr3? Again, we didn't show that mechanism, but yes. Oxygen attacks phosphorus, kicks off a bromine. A little bit different though. And the bromine comes back and attacks and kicks off the oxygen. Very similar to here, except you're going to have the oxygen bonded to a phosphorus. Again, you need to do it to see the differences. But see, to get the halide on there, you are attacking the carbon. By SN2, you should get inversion. So after step 1, we should get that. Now we come in here with cyanide. And now we can come in here and kick that off. And what does that do? We had 2 SN2s along the way. Since we had SN2, it's like we do double inversion and we're back to the original kind of stereochemistry. Now what's the difference? If we did this below, but instead first reacted with tosyl chloride, what would be the product?
Do you end up with a racemic product?
No, it wouldn't be racemic, it would be,
Instead of
it would be that. Because down here, whenever we convert this to the tosylate, what does the tosylate look like? I don't have room, or I could, I'm going to come this way. The tosylate will look like what? Right? Whenever you make tosylate, do we get any change in stereochemistry? No, when you make tosylate, there's no chemistry at the carbon. But now when we come in with cyanide, now we do a single inversion. If you do one inversion, you end up with, in this, as shown, dashed. But if you do two inversions, you go back to bold, right? As shown. The key thing here is, PBr3 converts this to the alkyl bromide, but you're going to get inversion if you know the mechanism. Because the bromine comes in and attacks the carbon. That's how it gets bonded to the carbon. But when you make tosylate, there's no chemistry at the carbon, so you don't get inversion. Everybody with me? How do you make OH a better leaving group? There's actually more than two ways. We say protonated, convert it to a tosylate. What's another way to make OH a better leaving group? No, that would make it a better leaving group, make it a better nucleophile. How do you make OH a better leaving group? Convert it to a bromine. Now we're not doing nuclear chemistry here, so we didn't really convert it. We replaced it with a bromine. That's what we did here. We replaced it with a bromine. Now it's a better leaving group. Everybody agree? Yeah. That's kind of what we did there. It's another way to move along and get to where you want to go. Maybe you don't have any tosyl chloride, but you got some PBr3. So, okay, it's just options. Everybody with me, young? Okay, so understanding the stereochemistry, dehydration of alcohols to alkenes. So I send you an email. The nomenclature of alcohols and ethers is indeed online video. Yeah. Okay. Dehydration of alcohols. Green sheet. What are we doing next after substitution?
Elimination.
Elimination. What are we going to eliminate? Water. And when you eliminate water, it's called a dehydration reaction, right? And dehydration reactions of alcohols lead to what type of product? Typically alkenes, and we saw this in Organic 1. Not in the context of alcohols or alkenes, but I showed it as a common elimination mechanism. And E1. I know it's E1. Typically done with acid, because how do you make OH a better leaving group? Acid. Is it E1 or E2? The OH is left, we're doing elimination. It's E1, of course, because E2 requires what? E2 requires a strong base. You have a strong base with sulfuric acid? No, that's the opposite of strong base. That's a strong acid. So it can't be E2. This is the classical E1 mechanism, okay? E1 mechanism. Very common. First step is protonate the alcohol. I assume you all can do that. What's next?
Just leave, right?
Do we have a nucleophile? I'll show that condensed, although we're not going to do a mechanism with it. If you ever do mechanism, you never use condensed structures. is sulfate, that's called bisulfate, hydrogen sulfate. Is that a good nucleophile? No, an organic one I said never will react. Now if we had like a Br minus, that would be a decent nucleophile. But sulfate, no. So there's no nucleophile. No nucleophile. So what can this do?
It just comes off.
The only thing it can do is just ionize. And if it ionizes, what do we get? Carbocation plus water. Can I show it like this? Instead of plus water, show a minus water on the line. Now, what can happen to this? A nucleophile could attack and give a substitution, but I told you there's no nucleophile. Never use bisulfate as nucleophile. What else can this do? It can act as a base. Actually, that's not quite right. Water actually acts as a base. Now, if I put in double bond right here, these two groups will be sort of cis, as drawn. Probably shows trans, not cis. That's because what's going to happen here? This is going to rotate, right? Because right now, this is called syn. Remember the models? Syn, rotate it, and they go anti. Which is preferred? Anti is preferred. Okay? And so this is going to rotate. Or instead of doing that, that kind of means action, rotate. Instead, it's going to go here and set up an equilibrium between syn and anti. But then, got H's here. Now this is where there's variability, and I am going to use the bisulfate as base. This takes one of the H's. These electrons move in. What does that do? You can draw your arrow however you want to get there, but that gives this, right? Plus what else? Sulfuric acid reformed. Thus the sulfuric acid was a catalyst. And this is a acid catalyzed dehydration reaction. What mechanism did we do? E1, carbocation. Carbocations are prone to rearrangements. That's not going to rearrange though. No rearrangement possible here. If you did a hydride shift, it'd be the same carbocation. Questions about this? I see some issues here. What do you want to ask about here? Is that how you guys did an E1 in Dr. Agee? Did you use bisulfate as a base, even though that's wrong? You use that as a base? Okay. Did he tell you it was wrong? How do you know what's wrong about it? It's not a good base. But you don't need a good base to do the second step of the E1. What's actually more appropriate to use as the base here instead of this?
Water.
Water, yes. Yes. Use water to take the H. Use water to take the H, what do we form? H3O plus, and this thing just sits with it. That's it. It's ionized. It's a salt. But guess what? Isn't that how sulfuric acid exists in water? So isn't that strictly more correct? Yes, it is. Because sulfuric acid is aqueous. This is how it exists. And it may be even more ionized than that. This could definitely ionize. But the first ionization is the strong acid part. The second ionization is a weaker acid. Okay? So water is actually more correct. Because that's actually how it exists at the end, so you should show it that way. But I told you in organic 1, I like to use the actual conjugate base so I can actually reform the thing that kind of is shown here and you can actually see how the acid is being reformed. I think it's a little bit more clear, even though it's not strictly correct. Using water is strictly more correct. You can do it either way you want. Okay? But if you're going to use this, please, you need a full structure. Do not use a condensed structure. Because a condensed structure, you cannot show precise error movement. Okay? All right. Common reaction. What was the terminology we used for elimination reactions? Double bond substitution. You remember Zaitsev and Hoffman? E1 always gives which product? Zaitsev. That is, why did we put the double bond on the end down here? Why didn't we make this alkene, which would be called what product? Hoffman. Why didn't we make the Hoffman? Because E1 always gives Zaitsev. More broadly, E1 always gives what?
The most stable.
The most stable alkene. Okay? Which of these three is the most stable alkene? The one shown, not these two. Not only is it Zaitsev, but it is also, in terms of stereochemistry, trans. Trans is more stable than cis. In the end, E1 always gives the most stable alkene. Ultimately because it's an equilibrium reaction. Okay? It's actually an equilibrium reaction because guess what? An alkene, if we came this way, we would be hydrating it. Alkenes can be hydrated to alcohols. Out with sulfuric acid. Actually in equilibrium. You can go both ways. Okay? Product below. Now, HF is commonly used for E1s. Because F minus is also a 4-nucleophile. Okay? So this is going to be an E1. All right? You need to make sure you understand why. Okay? But since it's E1, show product. I didn't pass out handout. Please pass around. E1. Everybody got it? Can you name your product? I won't come looking. Name it instead. Somebody name it? Should be pretty easy to name.
1-methyl-cyclohexene?
Yes. 1-methyl-cyclohexene. I agree? HF was the catalyst. Make sure you understand why. We can show the F minus taking that H in the mechanism, like I showed. Okay. Plus what? What else is made here? Water, right? Dehydration reaction. Okay? Produced water here. Right? And we're doing dehydration reactions. You can do one for homework up there. Using pocylpyridine. Lab tomorrow and Friday, we'll be checking in. We'll meet upstairs. Okay, you have the check-in instructions in the lab manual. Okay. Please read and follow guidelines, requirements. After check-in, we'll have lab lecture. Okay. Downstairs on that side, probably in the room. Other ways to dehydrate. What is B? What was A? A and B sounds like we're under something. What are we under? Dehydration. Another way to dehydrate alcohols is using POCO3, which I call, most people call pocylpyridine. Okay? trying to dehydrate a primary alcohol can be difficult using just sulfuric acid. Protonate ionides make a primary carbocation? Not likely. And you certainly can't dehydrate an alcohol by E2. E2 requires a strong base. What if we just use a strong base? Is this going to eliminate? No, because OH is a bad leaving group. How do you make OH a better leaving group? A variety of ways. Convert it to a bromine. You have to have acid to make it a good leaving group, but if you've got acid, you can't also have a strong base. So if you think about it, you can't do an E2. But you don't want to do an E1 becomes its primary. An alternative is to use pocylpyridine. And we'll look at that. Very similar to our previous reactions with like PCl3. This is going to react with the phosphorus and become positive. Then the pyridine will act as a base and eliminate off that positive oxygen. Okay? And we'll do that mechanism next time. We'll also be moving on to what's next? A synthesis of ethers. Please be looking ahead. Okay? Please be looking ahead. After ethers, we'll be moving on to epoxides, and I gave you that handout today. See some of you tomorrow for lab.